Let's talk about everybody's favorite thing in the whole world, fractions. So let's begin with the definition. Make sure we all know the correct terms for things. Definition. If A over B is a fraction, then A is the numerator and B is the denominator. The numerator is on top, denominator is on the bottom. Whenever you have a fraction, you can think of it one of two ways. It is either a number, or you can think of it as a division problem. Meaning, if I have the number 1/3, well, it's a number, it's the number 1/3. But you can also think of it as 1 divided by 3. When you think about a fraction, physically what you should be thinking of is you have an object. In fact, let's use 1/3 as an example here. 1/3. When you have an object, you can break it apart into pieces. That's what the denominator tells you. It tells you how many pieces your object was broken into. So let's say I have 1 square. Okay, well I can break that square into 3 pieces. In fact, 1, 2, 3 right there, the way it's drawn. Okay. So this tells you the total number of pieces that your object is broken into. Oh, that should be P-I-E. There we go. Here, let me do that again. Total pieces. Okay. Now, the numerator tells you out of those 3 pieces, how many of them are we considering? How many of them are we taking as part of our problem? So here, out of 3 pieces out of this object, only one of them is one that we're considering. Okay. When we talk about fractions, there's a few different ways in which we might write our fractions. There's a few different forms that fractions might take. First of all, we can talk about proper fractions. A proper fraction is where the numerator is less than the denominator. So something like 2/3, something like 5/8. These are proper fractions because the numerator is less than the denominator. If your numerator is equal to or bigger than your denominator, then you have an improper fraction. Now, the name's a little misleading, proper and improper. It makes it sound like one is better than the other. These are just names. There's nothing wrong with an improper fraction. There will be times where our answer will be an improper fraction. There's nothing wrong with one of these. It's just a label. It's just a name. Things like 7/3, things like 6/6. These are improper fractions because the numerator is equal to or greater than the denominator. Oops. Equal to or greater than the denominator. Okay. And then the third category is what's called a mixed number. Now, a mixed number isn't a different kind of fraction. Rather, a mixed number is what you get when you combine a whole number and a fraction by adding them together. So if, for example, you were to take the number 2 as a whole number and the number 2/3 as a proper fraction, 2 plus 2/3, and add those together, here you would get a mixed number. When you write a mixed number, you generally just write these together without a plus sign in between. So if you have a whole number, like 2, and you add to that a proper fraction, you wouldn't use an improper fraction for a mixed number. If you have a whole number and a proper fraction added together, the way we write that is, you essentially just don't write the plus sign in the middle, and you write that as 2 2/3. 2 2/3, a mixed number, we're generally not going to use these for computation. These are used for intuitive way of speaking about numbers. Meaning, if I have 7/3, that's easier to work with in algebra and arithmetic. However, 7/3 is not something that you can immediately visualize without having to think about it. But if I tell you 2 1/3, that's something a lot easier to visualize. 2 1/3 is 2 plus a little bit more. Right? So mixed numbers are meant to make your answer look nice, so that people can understand what you're saying with the least amount of work possible. However, they're not used much for computation because in order to use these, there's extra work to be done. So for the most part, if we're actually doing any kind of math, algebra, or arithmetic, we're going to be using proper or improper fractions. Mixed numbers are really only used for display. Once you have a final answer, everything's been done, then you can write it this way to make it a little easier for your result to be read. Now, fractions are just numbers, just like any whole number, except that, well, they have two parts, a numerator and a denominator. But otherwise, they are just regular numbers. What that means is anything I can do with a regular number, I should be able to do with a fraction. I should be able to add them, subtract them, multiply them, and divide them. Well, in order to do all of those things, there's one procedure that we need to know how to do first because it's used in every one of those operations, in addition, subtraction, multiplication, or division, and that's called prime factorization. So finding a prime factorization. Okay? When we say prime, we mean a prime number. A prime number is a number that cannot be divided by any positive whole number other than 1 in itself. So for example, the number 2. The only way to get 2, if you want to multiply two positive numbers to get 2, the only way to do that, the only way to multiply two positive whole numbers to get 2 is 1 and 2. Same thing with 3. The only way to multiply together two whole numbers to get 3 is 1 and 3. Now 4 wouldn't work, because yes, you could say 1 times 4, but you could also say 2 times 2. 5 is a prime number. 6 doesn't work because 6 is 2 times 3. 7 works. 8 wouldn't work because to get 8 you could say 1 times 8, but you could also say 2 times 4 or 2 times 2 times 2. 9 doesn't work. That would be 3 times 3. 10. 11 works. 13 works. And 17 works, and so forth and so on. There is no end to the prime numbers. If you started listing them, you would never finish because there's always more prime numbers that we can find. But these are just the first 7 of them, and these we'll be using more often than any others because they're smaller and easier to work with. So here, these are prime numbers. And again, a number is prime if you cannot divide it by any whole numbers other than 1 or itself. These are prime numbers. So a prime factorization involves these numbers. Factorization means breaking it apart into factors. Or in other words, breaking a number apart in a way that you multiply numbers together. That's when you multiply numbers, they're called factors. You want to break it apart in such a way that using only these numbers, you can multiply together to get the number you started with. So for example, let's go ahead and find the prime factorization of, let's start off with a small number, let's say 12. Okay, now 12 is not a prime number. It's not on this list, first of all. But also, even if I didn't have this list, I could say, well, I know numbers other than 1 and 12 that I can multiply to give me 12. It's true, 1 times 12 works, but so does, let's say 2 times 6. So here, I'm going to go ahead and break this apart this way. It's called a tree diagram. It's a useful way to organize this information. Here I'm going to say 12 splits into 2 and 6. When we say it splits into those numbers, we mean 2 times 6 is equal to 12. You don't want to add or subtract. This is multiplication. Now 2 is a prime number. Right here it's on that list. Yeah? But 6 is not, which means 6 can be factored some more. Okay, what numbers multiply to give me 6? You say, well, 1 times 6. Well, yes, but again, we want numbers other than those. Oh, well, 2 times 3 work. 2 times 3 is going to give me 6. And I note that 2 and 3 are prime numbers. So here, this is a prime number, but this one's not. So this one got split up further. This got split up into these prime numbers. So when we're done, our prime factorization is all the prime numbers that we get. Not the 6. That one's not a prime number. We get all of the prime numbers that we get that multiply together to give us the original number. In this case, our prime factorization is 2 times 2 times 3. Notice these are all prime numbers, and 2 times 2 is 4, times 3 is 12. Prime numbers that multiply to give you 12. Okay? The order here doesn't matter. If you had put the 3 first, that's okay. Put the 3 in the middle, that's fine too. Order of these doesn't matter as long as you have these numbers. Okay? Let's see that again. Another example, we're going to find the prime factorization. Let's go with a number a little bit bigger. Let's say 72. Okay? That's not a prime number. You say, well, my list didn't go up that high. Well, it doesn't have to. Since it ends in a 2, I know that's an even number. Anytime something ends in 0, 2, 4, 6, or 8, it's an even number, which means I can divide it by 2. All right, so 72 is what? 2 times 36. And if you don't remember that off the top of your head, you can always do the division. You can say 72 divided by 2. 2 goes into 7 3 times. 3 times 2 is 6. Subtract gives you 1. Drop your 2. 2 goes into 12 6 times. 6 times 2 is 12. And that's our result. Now, we know 2 is a prime number. It's on that list. 36, again, it ends in 0, 2, 4, 6, or 8. So we know it's even. So we could say 2 times, well, again, you can do the division. Or if you know it's 2 times 18, that's fine. You do 2 times 18. Now, you might say, well, what if I didn't use 2 and 18? What if I think of 2 other numbers besides the one you thought of? That actually is fine. It doesn't matter what numbers you use. All that matters is that you continue until you get a prime set of numbers. We'll see that here in just a moment. I'm going to go ahead and complete it using one set of choices, and I'll do the exact same number using a different set of choices, and we'll compare those. But for now, I'm going to use my first thought, which was 2 times 18. Okay, so again, 2 is a prime number, but 18 is not, which means we keep going. As long as we have numbers that are not prime, that means we keep breaking them up. Okay, well, let's see, 18, again, that's an even number, so I could say that's 2 times 9, and 9 is 3 times 3. So notice I don't use any of these. They weren't prime. We only want the prime numbers that multiply together to give us 72. So there we go. The prime factorization of 72 is 2 times 2 times 2 times 3 times 3. 2 times 2 times 2 times 3 times 3. And if you write these in any other order, that's fine too. If you want to write the 3's first and then the 2's, or if you want to do 2, 3, 2, 3, 2, that's okay. Any order is fine, as long as you have those numbers. Now, if you chose a different order, it won't actually make any difference. Let's see that again. 72. Let me make a completely different set of choices. All right, let's see. 72. Well, that's 8 times 9, isn't it? 72 is 8 times 9. That's different from how I started before. Before I said 2 and 36. Okay, so far it looks very different. But if I continue to separate these, notice neither of these are prime numbers. Okay, well, let's see. 8 is 2 times 4. Okay, well, 2 is a prime number, but 4 is not. So I can factor the 4 some more. That's 2 times 2. And 9, no, that's 3 times 3. Okay, so here I separated that into these two numbers, but they were not prime. Okay, let's see. Here the 2 is prime, and the 3, and the 3, and the 2, and the 2. And notice that even though we made different choices, the numbers in the middle are different. Even the pattern looks different. At the end, we still get 2 times 2 times 2 times 3 times 3. So if you make a different set of choices from someone else, it doesn't actually matter. As long as you factor until you're left with only prime numbers, you will still get the same result. So go ahead and give this a try. Go ahead and give this a try with the number 48. Go ahead and take the number 48 and perform this procedure. Go ahead and find the prime factorization. Pause the video, and once you have an answer, go ahead and unpause and we'll go through it together. All right, so let's take a look. Let's see, 48. Well, let's see, 48 is, well, I have a few choices. I could say 2 times 24. That would work. I could say 4 times 12. That would work. I could say 6 times 8. That would work. Any of those are fine. I'm going to go with 4 times 12. Why? Just I have to make a choice, and that's the choice I've made. All right, now 4 is not a prime number. I can separate 4 into 2 times 2. Oh, but now the 2's are prime, so I'm done with that track. Here, 12 is not a prime number. Oh, but I can factor 12. 12 is, well, they're going to have a few choices. I could do 2 times 6. I could do 3 times 4. Again, it doesn't really matter which way we go. I'm going to go with the first one I said, which was 2 times 6. Okay. All right, well, again, 2 is prime, but 6 is not, so I can separate that into 2 times 3. And if you know, again, we don't worry about these. They're not prime. We only want the prime numbers that multiply to give us 48. So here, the prime factorization, 2 times 2 times 2 times 2 times 3. Notice those are all prime numbers. They come from this list. And 2 times 2 is 4. 4 times 2 is 8. Times another 2 is 16. 16 times 3 is 48. So that works out. This procedure we've just seen is called finding the prime factorization of a whole number. This procedure will be used in just about any computation that we do that involves a fraction. Let's begin with simplifying. It's not actually an operation. We're not adding, subtracting, multiplying, or dividing anything. We're simply writing a fraction in lowest terms. Let's see how we can use a prime factorization to do that. Let's begin with an example. Let's reduce the following fraction. 16 over 84. Now, this is a fraction. But there are other ways to write this same fraction. We could multiply the top and bottom by 2, and that would give us 32 over 168. And even though those two numbers are different, they would mean the same fraction. All right? Going back to fractions that we had before, here was the number 1/3. If I went ahead and split each of these in half, and now instead of having 3 pieces, now I have 6 pieces. Okay, so my denominator is 6. And out of those 6, 2 of them have been shaded. So 2 over 6. But notice that even though I've used different numbers, it's still the same amount of my object. I still have my square, and I still have that much of my square. If I went ahead and split this even further and said this, okay, well now I've split it into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 pieces. And out of those 12, 1, 2, 3, 4 are shaded. And again, even though I have different numbers, all of these mean the same thing. 1/3, 2 6, and 4 12s are all the same amount. But this one uses the simplest numbers to write that expression. All 3 of these mean the same. But if I had to work with one of these, I'd rather work with this one because it's got the smallest, simplest numbers that I can get away with. This is your fraction in lowest terms. So that's what we want to do. We want to reduce the fraction in lowest terms. There are lots of ways of writing this fraction, but we want the simplest way possible. Let's use a prime factorization to do that. Let's take the number 16. All right, well, let's see. How do we factor 16? I can do 4 times 4. That would work. Now, 4 is not a prime number, so I can separate this as 2 times 2. And likewise, that one is also 2 times 2. And now, all of these are prime. Not those. They're not prime numbers. Only these. So multiply 2 times 2 times 2 times 2 to give you 64. Oh, sorry, to give you 16. Which means that that's the factorization of your numerator. 2 times 2 times 2 times 2. We can do something similar to 84. Let's see here. 84, I can factor that as 7 and 12. Now 7 is a prime number. It's a useful thing if you don't know your prime numbers to memorize at least the first few of them, the first 7, because we're going to use these a lot. 7 is a prime number. It is on that list, but 12 is definitely not. So we can factor 12 some more. 12 is 3 times 4. And, well, okay, well now 3 is a prime number, but 4 isn't. So I can factor that as 2 times 2. Okay, so there we go. We don't include these. They were not prime. Only the numbers that are prime, like that. So that's going to be 2 times 2 times 3 times 7. All right, now, once we've written the prime factorizations, notice that some of these numbers divide out. 2 divided by 2 is the number 1. Same thing over here. 2 divided by 2 is the number 1. Nothing else divides here. 2 divided by 3 is not 1. Right? So what's left? Well, in my numerator, 1 times 1 times 2 times 2. Okay, well, 1 times 1 is still 1, but 2 times 2 is going to give me 4. Down here, 1 times 1 is still 1, times 3 times 7 is 21. So these two mean the same thing, but now since here I've divided away everything that was redundant, I divided away everything that I didn't need, and left only the ones that couldn't be gotten rid of, this expression is in lowest terms. So to reduce a fraction to lowest terms, we factor out the numerator and denominator, divide out whatever's common, and whatever's left is our result. Okay? So go ahead and give this a try. Let's do 42 over 126. Go ahead and give that a try. Pause the video and use this technique to write this fraction in lowest terms. All right, so let's take a look at this. We're going to take 42. We're going to factor that out. 42. We can say 42 is 2 times 21. 2 is already a prime number, but 21 can be factored as 3 times 7. Oh, and that's it. Those are both prime numbers. Okay, so that's going to be 2 times 3 times 7 over 126. That's, well, let's see, that ends in a 6. So that's an even number. So that'll be 2 times 63. 2 is already a prime number, but 63 can be factored as 7 times 9. 7 is already a prime number, but 9 can be factored one more time as 3 times 3. And those are prime. So now the denominator factors as 2 times 7 times 3 times 3. Again, order doesn't matter. Any order you like. You want to put 2 times 3 times 3 times 7. As long as you have those 4 numbers, it's all the same. So 2 times, I'm just going to put it in the order I have here. 2, 7, 3, and 3. And now, if I reduce this down, 7's divide out, which is 1. 3's divide out, which is 1. And the 2's divide out, which is 1. And now, what am I left with? Well, my numerator is 1 times 1 times 1. Well, that's just 1. My denominator, 1 times 1 times 1, that's 1, times 3 is 3. And there we go. 42 divided by 126 is equal to 1/3. Just like that. Whenever we write a fraction, we want to write it in lowest terms. So whenever we perform a problem, whenever we perform an operation, we add, subtract, multiply, or divide fractions. In the end, even if we're not asked to, our answer should be in lowest terms. So if I finish multiplying 2 fractions and that's my answer, I'm not done. I should continue until I get lowest terms. If I add 2 fractions and I get this answer, again, I'm not done. I continue until I write things in lowest terms. Even if it's not part of the instructions, even if you're not directed to do that, that is generally the accepted result. All right? So now let's take a look at some operations. Let's take a look at taking fractions and adding, subtracting, multiplying, and dividing, keeping in mind that this will always be part of it. All right? Let's start off with multiplication, because multiplication is, out of all the operations that involve fractions, the simplest. When you add or subtract fractions, you need to find a common denominator. Multiplication, you do not. So that'll take a bit less work. Okay. Whenever you multiply fractions, if you have a fraction like a over b, and you multiply it times a fraction c over d, you just go right across. A times c, that's your new numerator, and b times d, that's your denominator. And that's it, you're done. Okay. Now, of course, if that product can be reduced, well, then you still have to do that. So let's consider some examples here. Let's start off with the simplest one where nothing needs to be reduced. Let's say I have 1 over 3 times 1 over 4. Okay. 1 times 1, well, that's going to be 1. And 3 times 4 is 12. And that's it. That's our answer. Here, nothing needs to be reduced because in order to do the reduction, we would factor things out. Notice 1 doesn't factor. There aren't any two whole numbers that multiply to give me 1 because 1 is just 1 times 1 and that's it. So here, nothing would be reduced. Okay. Let's talk about one where you do have to reduce. Let's say I have 2 over 9 times, let's say 3 over 8. 2 9ths times 3 8ths. Okay. In order to do this, there's two ways you can go about it. You can start by multiplying these together first and then reducing, or you can reduce first and then multiply. It doesn't really matter which way you go. You'll get the same answer. It's kind of a matter of preference. Here, let me show you both. One way to do it is to just go across. 2 times 3 is 6. 8 times 9 is 72. And now that I've multiplied, now I can reduce the way I was doing above. Okay. All right, well, let's see here. 6, well, that's 2 times 3. I don't need a tree diagram for that one. That's just 2 times 3. 72, that's going to be 2 times 2 times 2 times 3 times 3. You might say, wow, you did that really quickly. Not really. That was one of the examples we did a few minutes ago. All right, 72 was 2 times 2 times 2 times 3 times 3. 2 times 2 times 2 times 3 times 3. If ever you find something that factors a number, you don't have to keep doing it over and over again. It's the same result. All right? So we multiply these together, then we factor, and then you simplify and divide away. Let's see, 2 divides 2, that gives me 1 over 1. And 3 divides 3, and that's 1 over 1. And that's it. Here, you wouldn't divide these because they're both in the denominator. You need 1 in the numerator to divide 1 in the denominator. So now my result, 1 times 1 is 1. In my denominator, 1 times 1 is 1. Times 2, times another 2 is 4, times 3 is 12. And that's our result. 2 9ths times 3 8ths is 1/12. Okay. Now, you can go the other way. You can say, I want to simplify first and then multiply. Okay. So let's do the exact same example, but in the opposite order. And then you can decide which one you like the best. Okay. I'm going to factor things out as much as I can. 2 is, well, it's just 2. Right? It's already a prime number. Oh, but 9 is 3 times 3. Okay. 3, again, that's already a prime number. Oh, but 8 is 2 times 4. And 2 is already a prime number, but I can say 4 is 2 times 2. So 2, 2, 2. Okay. Now, when I multiply, what I'm going to do is I'm going to join everything in either numerator together as one numerator, and everything in one denominator joins together as one denominator. So here, I'm going to do that by just merging the two fractions together. Okay. The 2 times the 3 all comes together as one numerator. The 9 times the 8 all come together as a single denominator. But since they're all together, hey look, some stuff divides away. 3 divides into 3, and 2 divides into 2. And so 1 times 1 is 1. And here 1 times 1 is 1. Times 2 is 2. Times another 2 is 4. Times 3 is 12. And you notice that's the exact same answer that we had before. Okay. Some people like doing it this way because, all I have to do is go right across, then I can worry about simplifying later. Other people like this way because, my numbers are small, it's easy to simplify, and then I multiply. There's no better or worse way to do it. It's just a matter of which one do you like. Okay. So, go ahead and give this a try. You're going to multiply, and in the end, you're going to make sure it's reduced down to lowest terms. You can do it either way. You can multiply first and then reduce, or you can reduce first and then multiply. Okay? One bit of advice, though. When your numbers start getting bigger, it's usually a little bit faster to factor first and then multiply. Because if your numbers are bigger, if you multiply them first, they're going to get very big, and then they're going to be harder to work with. Okay? That's just a bit of advice. However, if you wish to do it that way, that does work perfectly well. All right, so give this a try by whichever method you like. Let's have you try. Let's do 6 over 25 multiplied by 15 over let's do 18. Okay. So go ahead and pause the video and give this a try. Once you have your result, go ahead and unpause and we can go through this together. Okay. I note that if I multiply 25 times 18, I'm going to get something pretty big. And I don't want to have to deal with big numbers. So I'm going to choose to do it this way, where I'm going to factor first and then multiply. If you multiplied first and then factored, that's fine. You'll still get the same answers that we're about to get. All right? So let's see. 6 is 2 times 3. 25 is 5 times 5. 15, that's 3 times 5. And then 18, well, let's see, 18, that's 2 times 9. 2 is already a prime number, but 9 is 3 times 3. Okay. So 18 is 2 times 3 times 3. Now remember, when you're multiplying, you're basically just merging all of this as one big fraction. So here I'm just going to draw one big division bar. And now, if anything simplifies, I do that now. Let's see, 5 goes into 5, that gives me 1. And 3 goes into 3, that gives me 1. And that 3 goes into that 3, so that gives me 1. And 2 goes into 2, that gives me 1. And that's it. So 2, 3, 3, 5. 2, 3, 3, 5. Those all divided away. So what's left? Well, my numerator is 1 times 1 times 1 times 1, which is 1. And my denominator is 1 times 1 times 1 times 5, which is 5. So in the end, 6 over 25 times 15 over 18 is 1/5. And that makes us happy. Now, before we go on, it's useful to have a visual as to what we mean when we talk about multiplication of fractions. What are we doing? What do we find when we say this times this is equal to that? What do we mean? When we talk about whole numbers, it's pretty easy to tell. If I say 2 times 3, well, that means I have something that comes in pairs, and I have 3 pairs. Here's one pair, a second pair, and a third pair. Well, obviously, it's 6. But what do I mean when I multiply a fraction times a fraction? Well, let's take a look at that. Let's say I have 2/3, and I'm going to multiply that by, let's say 4/5. All right. Now you say, well, I know how to do that. That's 2 times 4 is 8, and 3 times 5 is 15. Right. We know how to mechanically do it. We know how to find a number. But what are we doing? What did we actually find? All right. Well, let's see here. Let's say we have an object, a rectangle in this case, because, well, I'm not very good at drawing, and, well, that's something I can draw. Now, here's an object that's a whole object. Now, a fraction means I'm going to take part of this whole object. So I'm going to take 2/3 of this object. Okay, so I'm going to break it into 3 equal parts, or about as equal as I can get. I'm not going to break out a ruler here for this one. Here, these are meant to be 3 equal sizes. Okay? All right, now 2/3 means out of my 3 equally sized pieces, I'm going to consider only 2 of them. All right, so 2/3 is, let me continue to use the same color for this one. There we go. I have visually represented 2/3, 2 out of 3 pieces. All right, now, on that same rectangle, let me go ahead and consider 4/5. I want to go ahead and draw 4/5 on this right here. I'm not going to draw it vertically because I've already drawn this one vertically and it would be a little confusing to do it that way, so I'm going to do it horizontally. So 4/5 means I'm going to break up my rectangle. Ignore these vertical lines. Pretend they're not there. Pretend we just have a rectangle that we started with. All right. 4/5 means take that rectangle and break it into 1, 2, 3, 4, and 5. All right, that's one rectangle that was broken into 1, 2, 3, 4, 5 pieces. Now, out of that 1, 2, 3, 4, 5 pieces, I'm going to consider 4 of them. Okay, so here's 1. Here's 2. 3, 4 out of those 5. Okay. Well, if I look at both of these fractions at the same time, this broke up my rectangle into 3 pieces. This broke up my rectangle into 5 pieces. So total, if I look at both of them, they broke my rectangle up into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. They broke my rectangle into 15 pieces. Now, how many of those pieces have been highlighted? Again, we're looking at both of the fractions. How many of these have been highlighted by both fractions? In other words, how many of them are marked in blue and red? Well, I see 1 right here, and 2, 3, 4, 5, 6, 7, 8. Here, these aren't marked in blue. They're only marked in red. Here, these are not marked in red. They're only marked in blue. And this one's not marked at all. So, if I'm looking at both fractions at the same time, together, they cut my rectangle up into 15 pieces. And together, they shaded in 1, 2, 3, 4, 5, 6, 7, 8 out of those 15. 2 times 4, 8. 3 times 5, 15. That's what we're looking at when we multiply fractions. We're saying if we take both fractions and at the same time cut up our portion, what do they both do at the same time? If I have 2/3 of an object and I take 4/5 of that 2/3, how much did I end up with? Well, I ended up with 8 out of a total of 15. It's a little bit more involved than 2 times 3 equals to 6, but it still can be thought of as a physical thing. In any event, let's go on to our next operation. We've seen simplify, we've seen multiplication. Let's take a look at division of fractions. When we talk about divisions, we need to define one thing, and that is a reciprocal. So here's a definition. If A over B is a fraction, then B over A is its reciprocal. Here, a little note. 0 does not have a reciprocal. Because after all, 0 is like saying 0 over 1, but if you flip that upside down, then you have 1 over 0. And dividing by 0 is undefined. So 0 does not have a reciprocal. Every other number, you simply transpose the numerator and the denominator. You flip it upside down. So if, for example, I have the number 2/5, then the number 5/2 is its reciprocal. Don't write equals here. Don't say 2/5 equals 5/2. They're not equal. They're reciprocals of each other. Let's say you had a whole number, like 8. You say, well, how do I flip that? There's no numerator and denominator. Well, you can think of any whole number as itself over 1. So 8 is like thinking 8 over 1. And now I can reciprocate that as 1 over 8. And again, these are not equal to each other. These are reciprocals of each other. And you can do that for any number except for 0. Because if you have 0 over 1, reciprocating would be 1 over 0. And 1 over 0 is undefined. We don't have a meaning for division by 0. Okay? So if you're going to divide by a fraction, you're going to multiply by a reciprocal. To divide by a fraction, multiplied by its reciprocal. So let's see some examples of that. If you have 5/8 and you want to take 5/8 and you want to divide 5/12, then to divide, you're going to multiply by the reciprocal. What that means is you're going to rewrite this as the number you're dividing, you're going to leave that alone. The number you're dividing by, the second number, that's the one you reciprocate. So this division becomes multiplication. And then this second number, not the first one, the second one is reciprocated, 12 over 5. But now that you've reciprocated, change this to a multiplication, now this is just regular old multiplication, the way we've already seen. So here, now we can just multiply. Here, I'm going to go ahead and simplify first and then multiply, because I don't want to make the numbers bigger than they already are. Otherwise, that's going to make things more complicated than it needs to be. So I'm going to leave 5 as it is, because it's already prime. But 8 is 2 times 2 times 2. Those are all prime numbers. 2 times 2 is 4, times 2 more is 8. Here, 5 is already prime. 12 is 2 times 2 times 3. And if you join these together as one big fraction, you notice most of this divides away. The 5's divide away. The 2's divide away. And those 2's divide away. And so you're left with 1 times 1 times 1 times 3. That's 3 as your numerator. 1 times 1 times 1 times 2 gives you 2 as your denominator. And as we've mentioned, this is called an improper fraction. The numerator is greater than the denominator, and there's nothing wrong with that. We don't need to change this into a decimal. We don't need to change this to a mixed number. For the most part, whatever our answer is, whether it be a proper fraction, an improper fraction, or even a whole number, this is a perfectly acceptable answer. Note that whole numbers also have reciprocals. So, as another example, we could say something like 7, let's say 7/15, and we're going to divide this by the number 14. Okay? This is a fraction, because you can think of it as being 14 over 1. So now, instead of dividing by this number, we're going to multiply by its reciprocal. You're going to leave the 7/15 the way it was. Division will become multiplication. And now 14 over 1 gets reciprocated to 1 over 14. And now we can multiply. Here, 7 and 1 are already prime numbers. We don't We can't factor those anymore. 15 is 3 times 5, and 14 is 2 times 7. And it looks like not a lot divides out. It looks just like the 7s. So in the end, I have 1 times 1 equals 1 in my numerator. 1 times 2 is 2. 2 times 5 is 10. Times 3 is 30. So if I take 7/15 divided by 14, that's the same as 7/15 times 1 over 14, which reduces down to 1 over 30 as my result. So go ahead and give this a try. Do the following division. Let's do 5/16 divided by let's say 5/12. All right, give that a try. Go ahead and pause the video, and once you have a result, go ahead and unpause and we'll go through it together. All right, so let's take a look at this. We're going to leave the first number as it is, 5/16. Division becomes multiplication. Second number, we reciprocate. And now we're going to multiply and simplify. All right, 5 is already a prime number, so I'll leave that the way it is. 16, that's 2 times 2 times 2 times 2. All right. 16, that's 4 times 4. And each of these 4s splits up as 2 times 2. 2, 2, 2, and 2. 12, no, we already saw 12 a few times already. It's 2 times 2 times 3. And again, 5 was already a prime number. So if we merge all this together as one big set of fractions, like this, then we note that several of these divide away. 5s divide out, 2's divide out, and these 2's divide out. So we're left with 1 times 1 times 3, which is 3 in our numerator. 1 times 1 times 2 times 2 is 4 in our denominator. So if we take 5/16 and divide it by 5/12, that's the same as 5/16 times 12/5, which reduces down to 3/4. And that makes us happy. All right, now, the next thing we want to look at is addition and subtraction. We're going to look at those together because they work almost exactly the same way. In order to add or subtract two fractions, you need to find a common denominator first. Now, if you already have a common denominator, well, then you don't worry about that. You can skip that step. So our first example is going to be one where things are really about as ideal as we can hope for. Let's say we're going to add together 3/17 plus 5/17. These already have the same denominator. That's what we mean by common. They have a denominator in common. Whenever you have a common denominator, all you need to do is add the tops. 3 plus 5 is 8. The common denominator is just going to stay as it is. This is like saying I had a square or a rectangle. I cut it into 17 pieces and I took 3 of them. Oh, and then later on I took that same square that was cut out of 17 pieces and I took 5 of them. So total, out of those 17 pieces, I took 8 of them. All right, so the denominator doesn't need to be added or subtracted. Once you have a common denominator, you keep that same denominator throughout. It's only the numerator that gets added or subtracted. So for example, if I have 8/15 minus 1/15, again, they already have a common denominator. I don't need to worry about that. My answer will keep that same denominator. and all I have to do is do the subtraction. 8 minus 1 will give me 7. If I can then reduce that, well, then I should reduce it. But in this case, 7 is already a prime number. Nothing divides away. Here, 17 is a prime number. Nothing divides away. Right? If something can be divided, well, then we divide it. But what happens when you don't have a common denominator at the beginning? Well, then you need to find one. And again, using a prime factorization is the way to do it. So let's consider something like 1 over 6 plus 3 over 8. Okay? To find a common denominator, I want to find the prime factorization of my two denominators. If the numerators can be factored, that's fine, but we don't really care about that. We only worry about factoring the denominators. If the numerators can be factored or if not, it makes no difference. So generally, we don't even try. We just worry about the denominators. So here, 6 is 2 times 3. So I'm going to rewrite that as 1 over 2 times 3. And 8 is 2 times 2 times 2. 2 times 2 is 4, times 2 more is 8. So it's going to be 3 over 2 times 2 times 2. Like that. So now, once these are factored, we can use these to find our common denominator. Here's how it's going to work. We're going to need to find the union of these two sets. We're going to need to find the what now? Well, in order to explain this, I'm going to use kind of a silly analogy, but it is one that works pretty well. Imagine you have two kids. If you've never been around kids, one thing that you may not realize exactly to the extent at which it's true is they are very, very fair about everything, or at least they want to be fair as long as it doesn't inconvenience them. So if I were to have these two kids and tell them, okay, here are your toys. These are the toys that you can play with. And oh, here's another kid. And these are the toys you can play with. They're both going to be mad because they're both going to feel like it's not fair. This child's going to feel like, well, they got more toys than me. Look, he's got that many toys, and I only have this many toys. And this child's going to feel like it's unfair to them because, look, I only have the same toy, and here they get different kinds of toys. So they're both going to be very upset. All right? So what we want to do is we want to give them both the exact same set of things. But they already have some stuff, and another thing about a kid is if they already have something, you try to take away from them, they're not going to be happy about that either. So here, what I'm going to do is I'm going to slowly introduce new toys into both of their playgrounds until they both have the same amount of stuff. All right, so now, why is this child mad? Oh, because this child has a 3 to play with. Right? This child has more toys, but that's the toy that they're missing. So in order to make this child happy, I'm going to provide them a 3. Okay. Now this child is completely happy because look, this child has everything the other child has and extra stuff. So now they're perfectly happy. Incidentally, whenever you do something on the bottom, you're going to do the same thing on top. Okay, but now this child is now even more unhappy because obviously this child has a lot more now. Okay, well, what is this one still missing? Well, it's got a 2 and a 3, but they're missing a 2 and another 2. So let me give them a pair of 2s here. Again, whatever I do on the bottom, I do on top. Notice that now they all have what they started with, but by giving them the following toys, by giving them the following factors, they now have exactly the same set of toys to play with. 2, 2, 2, and 3. This is the common denominator. This analogy is a little simple, but it's one that's effective in helping people remember. The two children, if they have a different set of toys, are going to be very, very upset. So here we want to make sure they have the same set of toys. All right, so now with that analogy aside, let's see what we actually got though. 2 times 2 is 4, times 1 is still 4. Over 2 times 2 is 4, times 2 is 8, 8 times 3 is 24. Over here, that's the same thing. That's still 24. Here, 3 times 3 is 9. And so now you have a common denominator. Now you can just add the tops. 9 plus 4 is going to give us 13 over 24. Here, we're not going to bother to reduce because 13 is already a prime number. It doesn't go into 24, so we know we're done. So that is our result. That procedure might seem a little bit long and it might seem a little bit complicated, but it mostly just takes some practice. So let's see that again. Incidentally, once we get past the story of the two kids in the toy boxes, it's actually not quite that long of a procedure. So let's go ahead and do another example together here. Let's do 5 over 18 minus, let's do 5 over 24. Like that. Okay. Again, plus or minus is going to work the same way. The only difference is at the end, you're going to subtract the two numerators instead of add them. Otherwise, it's all the same. So here we go. We're going to factor the denominators into a prime factorization. If the numerator can be factored or not, it makes no difference. In fact, we don't really even bother. Just leave it the way it is. The denominators, we're going to go ahead and factor. All right, well, let's see here. 18, let me do it over here. 18 is 2 times 9. And 2 is a prime number already, but we can factor 9 as 3 times 3. All right, so that's going to be 2 times 3 times 3. 24, we can factor 24 as 3 times 8. Now 3 is already a prime number, but 8 can be factored as 2 times 4. And 2 is already a prime number, but 4 can be factored as 2 times 2. So in the end, my factorization of 24 is 2, 2, 2, 3. 2, 2, 2, 3. Okay. So now we want to make the denominators the same. What is this one missing? Again, your children, they don't have the same set of toys. What is this one missing that the other one already has? Well, this one has more 2's than this one does. Okay, how many more? Well, this one only has 1 2. This one has 3 2's. Okay, so I need 2 more of them. So multiply by a 2 and another 2. And whatever I do at the bottom, I do on top. Okay, so now this has everything the one on the right does. It's got a 2 and a 2 and a 2 and a 3. But now this one's missing something. I think your child is missing one of the toys that this one has. Yeah. Here, you need another 3. Whatever you do on the bottom, you do on top. Notice the denominators are now exactly the same. 2, 2, 2, 3, 3. Okay, so now we can put that together and finish our problem. 2 times 2 is 4. 4 times 2 is 8. 8 times 3 is 24. 24 times 3 is 72. So that's going to be our common denominator. Both of these have a 72 in the denominator like that. And now our numerator, 2 times 2 is 4 times 5 is 20. Minus 3 times 5 is 15. And now we subtract. 20 minus 15 is 5 over 72. And that is our result. If you take 5/18 minus 5/24, you end up with 5 over 72. If you take 1 over 6 plus 3 over 8, you end up with 13 over 24. So give this a try. Oh, let's see here. Let's have... Let's give that a try. 6 over 35 minus 2 over 21. Go ahead and give that a try. Pause the video, and once you have a result, go ahead and unpause the video, and we can go through that together. All right, so let's give that a try. We're going to go ahead and factor out the denominators. Notice here the numerator 6 can be factored. That doesn't matter. We don't ever worry about factoring the numerators when we add or subtract just the denominators. So here, let me leave 6 the way it was. 35 is 7 times 5. Here, let me leave 2 the way it was. 21 is 3 times 7. Okay, so now we want to give these a common denominator. This one already has a 7 like that one does, but it doesn't have a 3 yet. So let's go and multiply this by 3, and whatever we do on the bottom, we do on top. Here, that's already got a 3 and a 7, but it's missing a 5. So let's multiply both top and bottom by 5. And so now you have the exact same denominator. You have 3 times 7, 21. 21 times 5 is 105. So that's our common denominator. Our numerators are now 3 times 6 is 18. Don't forget to multiply it on the bottom and on top, at the same time. Well, the most common mistake that we see whenever we have people adding or subtracting fractions incorrectly is they'll only worry about the denominator and they'll forget to change the numerators. If you're changing the denominator, the numerator will also change in the exact same way. Here, 2 times 5 is 10. And so now we can subtract. 18 minus 10 is 8 over 105. Here, can we reduce this? It doesn't look like it, no, because 8 is 2 times 2 times 2. 105, we already know what 105 is because here's the prime factorization. All right, we don't have to go back and find it. We already know what it was. It's 3 times 7 times 5. That's how we got 105 in the first place. And if you notice, there's nothing that divides out. Okay, so since there's nothing that divides out, we don't worry about that. Our result is 8 over 105. Incidentally, this has a name. Whenever you find the least common denominator by putting these factors in together, what you're doing is you're finding what's called the least common multiple of these two numbers. So a quick definition, whenever you find the common denominator, what you've really done is you found the least common multiple of your denominators. The least common multiple of two numbers is the smallest whole number that is a multiple of both. Least common multiple is a long phrase to say, so oftentimes it'll be abbreviated as LCM, using the first 3 letters, LCM. The least common denominator is really the least common multiple of the denominators, meaning it's the smallest number that's a multiple of 35 and 21. You can see that if you write out the times tables. 35 times 1 is 35. 35 times 2, that's 70. 35 times 3, that's 105. 35 times 4, that's 140. 35 times 5, that's 175. And 35 times 6, that's what, that should be 210, like that. Now if I write out the times tables of 21, 21 times 1 is 21. 21 times 2 is 42. 21 times 3 is 63. Times 4 is 84. Times 5 is 105. Times 6 is 126, and so forth and so on. Notice that the first number that you see that's on both of these lists is our common denominator, 105. It's the least, the smallest one that is common, that they both have on the same, that's on both lists. If you keep going, you'll eventually find more numbers that are common. You'll eventually find more numbers that are on both lists. For example, 210 is on both lists. If we keep going on this one, we'll eventually get there. But we want the smallest one. That does mean that if you write out the times tables of your denominators, you will eventually find the least common multiple of the denominators, or in other words, the least common denominator. However, that might not always be the best idea, because here we found it not terribly, it didn't take us a terribly long time to find. But if the least common multiple is very, very big, you might have to write out the times tables, not just from 1 to 3 or 1 to 4 or 1 to 5. It might take you from 1 to 200 to find the common multiples. So doing this is possible. It will work. It's just, depending on the numbers, might take you a very long time. Doing it this way, using the prime factorization, generally is much simpler. Okay. Finally, the last thing that we're going to talk about here is, at the very beginning, we talked about 3 kinds of fractions that we might see. That's the proper fraction, the improper fraction, and the mixed number. Proper fractions and improper fractions we've seen several examples of for addition, subtraction, multiplication, and or division. But we haven't really seen much about mixed numbers. That's because we don't really use mixed numbers in computation. As I mentioned at the beginning of the section here, we generally use mixed numbers for display purposes. Once you've done everything, then yeah, sometimes a mixed number is easier to understand than an improper fraction. 7/3 is maybe not as intuitive as 2 1/3. But when it comes to doing computations, mixed numbers are not really nice to work with. So what we do is we change them. We take a mixed number, change it to an improper fraction, and then once we have an improper fraction, then we can perform the arithmetic on that. So as our final bit for this section, let's go ahead and take a look at how to do that. So let's consider, well, I guess I should label this. Converting mixed numbers to improper fractions. And improper fractions to mixed numbers. Okay. To convert from an improper fraction to a mixed number, all we're going to do is we're going to perform the division that's stated in the fraction, and then write the answer using the remainder. So for example, let's go ahead and take eight thirds, and we're going to write that as a mixed number. So remember, this is an improper fraction because the numerator is greater than the denominator. And again, it's just a name. There's nothing wrong with this kind of fraction. But if you want to write it as a mixed number, here's how you do it. You're going to start off with 8, and you're going to divide that by 3. Numerator inside, denominator on the outside. 3 goes into 8 twice. 2 times 3 is 6. Subtract, and you get a remainder of 2. So your mixed number is going to be 2 and 2/3. This number up here is going to be the whole number. This remainder will be your numerator. And this divisor will be your denominator. So your answer is 2 2/3. Give that a try. Go ahead and convert let's say 12 sevenths. Go ahead and convert that to a mixed number. Go ahead and pause the video, and once you have a result, go ahead and unpause and we'll go through it together. All right, so 12 divided by 7. 7 goes into 12 only once. 1 times 7 is 7. You subtract gives you 5. This number up here, that's your whole number, 1. The remainder is your numerator, 5. And the divisor is your denominator, 7ths. So 12 sevenths is 1 5/7. What you're saying is, if I have 12 objects and I break them up into 7, well, that's one group of 7 and then 5 left over. Right? 7 and then the extra 5 gives me 12. That also shows us how to go in the opposite direction. If we want to go from a mixed number to an improper fraction, that's what we're doing. Notice here, that's one group of 7. So 1 times 7 is 7, plus the extra 5 gives us the 12. So it's the whole number times the denominator plus the numerator. Let's say we're going to convert a mixed number, 3 5/6, and we're going to convert that into a mixed, into an improper fraction. Again, the pattern is you take your whole number times your denominator. That was this result here, this 7, and then the remaining 5 gets added in. 1 times 7 makes 7, plus 5 make 12. So here, you're going to take your 3 times your 6, whole number times your divisor, and then, since that 5 was left over, that gets added in over your divisor. So 3 times 6 is 18, plus 5 is 23 over 6. And that is our improper fraction. So we can go back and forth. If ever you need to add two mixed numbers, or multiply, or divide, or anything else, if you're going to do arithmetic with mixed numbers, the first thing you do is convert it to an improper fraction. Once it's an improper fraction, then you can do all the stuff we've done so far in this video to add, subtract, multiply, or divide. So give that a try. Remember the pattern. It's whole number times the divisor plus the numerator. Your divisor stays the same all the way throughout. So give this a try. If you have the number 2 1/8, go ahead and convert that to a mixed number. Pause the video, and once you have a result, unpause and we'll confirm it together. All right, so that's going to be 2 times 8, your whole number times your divisor, because there's 2 groups of 8, which gives us 16, plus that extra remainder, 16 plus 1 is 17. Your divisor remains the same. So 2 1/8 is 17/8. And that is the end of our section. If anybody has any questions, comments, or problems over fractions and the arithmetic of fractions, please let me know. And I hope you all have a nice day.